Hello guys. So most of you would have heard the term semiconductors. So what are semiconductors? So as the name suggests, it is not a conductor and not a fully an insulator also. It is somewhere in between. So what is the basic difference between these three? It relates to the energy band gap between the valence band and the conduction band. So let's start with the basics. So there's an atom. We know that the outermost shell has electrons, of course, and that shell is called as a valence shell, and the band related to that is the valence band, and the electrons in that is called valence electrons. Now, when these valence electrons get enough energy to go to the conduction band, which is beyond the outermost shell, that leads to conductivity. And in conductors, the uh, valence band and conduction band kind of overlap, so conductivity is very high. In insulators, the band gap is very large, and in semiconductors, it is somewhere in between. It just needs enough energy for the electrons to go from valence band to the conduction band. Now, whenever an electron goes from valence band to the conduction band, it means that it has acquired some energy. And whenever an electron goes from conduction band to the valence band, that means it has uh, transmitted energy. So that is the basic concept. So what are the types of semiconductors? What is the material utilized? So silicon is a pure semiconductor or intrinsic semiconductor. It has four electrons in the outermost shell, but it's not efficient enough, so much so as to use it in in an electronic device. It has to be made or converted into an extrinsic semiconductor with the help of a dopant, a doping material, or an impurity. So the impurity can be a trivalent uh, atom-based element or a pentavalent atom-based element. So trivalent atom would be like boron or uh, say indium, and pentavalent would be phosphorus, arsenic, antimony, so on and so forth. So what happens is in trivalent there are three electrons in the outermost shell, and when it is combined with the silicon element, so it combines with the three atoms of or three electrons of the silicon atoms, but there is a hole which remains. It doesn't form a covalent bond. So what happens is silicon atom donates an electron which occupies that vacancy, right? So basically the current is flow of current is due to the holes in this case, and this leads to a formation of a p-type semiconductor, positive type semiconductor. In an n-type semiconductor, a pentavalent, that means an atom which has five electrons in the outermost shell, that is utilized. And once it is mixed with silicon, then the four electrons combine with the silicon atoms, but there is one electron which remains free. Once it gets enough energy, it moves to the conduction band for conductivity. So when this p and n regions are integrated, it forms a p-n junction. So let's not go into the details, but this p-n junction acts as a potential barrier which stops the flow of electrons from n-type to the p-type, and therefore the conductivity. But when is connected to a battery source, like when positive is connected to the p-type and negative part is connected to the n-type, it is a forward biased um, semiconductor, and when in the opposite case, it is the reverse bias semiconductor, when negative to p-type and positive to n-type. But the concept is that once the potential is increased of the battery source, the barrier potential, which is zero point 0.7 volts in case of silicon, if that crosses, then there is a flow of current, and it can be utilized in applications. So basically, it is like semiconductors are like a faucet, like it's like a faucet which controls the flow of water. So similarly, semiconductor controls the flow of current. So this is what happens, and manufacturing and fabrication of semiconductors is a very complex process. And initially, I mean, of course, before coming to that, I want to talk about a few application, a basic application that is in the form of p-n junction diode or light emitting diode. Of course, there are transistors also, which is utilized in more advanced integrated circuits or hence electronic devices. But just an example or an application of semiconductors, let's talk about this LED. So light emitting diode, or say p-n junction diode. So what happens is The working is the same. Okay, so the transfer of electrons takes place for the conductivity to be there. So in normal electric lighting devices, electric energy is converted into heat and heat is converted into light. But in this case, electric energy is directly converted to light. So for example, when an electron goes from n-type region to p-type region and goes from the conduction band to the valence band, as I said earlier, it releases energy. So this energy is in the form of light, and the color depends upon the wavelength. So if it is a shorter wavelength, then we get a blue light, so and so forth. So this is a basic example, and that's why we say that that's how we say that a light emitting diode is more efficient. That LED lights are more efficient than the normal ones. Now, of course, there are, as I mentioned, transistors also. So the fabrication of transistors is also a complex process, and it is run by a few companies. Taiwan Semiconductor Manufacturing Company, it has the largest share in the market. There are other companies also in China, in Singapore, in Japan, but TSMC gets most of the contracts from companies across the world. So what it does is that it has a base in the form of a silicon wafer. It undergoes a purification process. Then it is coated with a light sensitive material called photoresist, and uh, a photolithography process is undertaken, where there is a mask, where there is a circuit design on that mask, and that is exposed to a light source. And when the light goes through the gap of the design in the mask, okay, some portions are carved and some portions are uncarved as far as the silicon wafer base is concerned. So the uncarved portions are removed with chemical or physical processes, and what remains is the circuit. But that is not enough, because we haven't added the dopant yet. So it is dopant is added, whether it is p-type or n-type, whatever, and accordingly extrinsic semiconductor is formed, conductor is formed, and uh, an integrated circuit ultimately is formed with a lot of transistors etched on that circuit, or the chip, with a complex process. For example, it requires a lot of precision. For example, consider a strand of hair. Let's say we are dividing into 1,000 parts, and then each part is again divided into 100 parts. So imagine how small it gets. And the integrated chips are like no longer than the size of a nail, human nail, a fingernail. So that's how complex it is. Now, because of the very few players in the market of fabrication, there are supply chain bottleneck issues. Now, for example, even the equipment used for photolithography is provided by a Dutch-based company, ASML. That is the sole provider. It's not even the largest provider; it's the sole provider. So this leads to challenges. For example, during the pandemic period, we saw how the sales of automobiles took a beating because the demand went down. Okay, but when the demand went up, demand for the cars went up, there weren't enough semiconductors which were affected by the supply chain crisis during the pandemic period, and there weren't any there weren't any semiconductors or integrated into those cars or automobiles. Thereby, the sales got affected. So challenges would be there, but there is a future. And when talk about future, the first thing which comes to mind is artificial intelligence in any space, in any domain. Of course, in semiconductor, uh, it is the same case. So, AI chips, which involves parallel processing, calculating, manipulating a lot of data. There's a lot of use cases also. So, for example, autonomous vehicles, which is the future, and so image detection, complexity of the environment, detection of that, decision making, a lot of things. So AI chips would be designed accordingly to take those decisions. Of course, there would be ethical concerns, but that's a different debate altogether. Then there is advanced robotics. I mean, in that also AI chips would be utilized. So the usage of artificial intelligence based semiconductor chips is only going to increase. So this was a gist of semiconductors and its applications, challenges, and the future aspects. I hope you liked the video. If you liked it, please click on the like button and do subscribe to the channel. Thank you very much.